Today, we will continue to talk about finite dimensional representations of affine quantum groups. And in some sense, okay. And the topic of today's lecture will be the notion of Q characters. Can I make it larger? Okay, I'm trying to do something with my laptop. If it broke for you, please tell me. Okay. Okay, people in Zoom, is everything okay?
Yes.
Yeah.
Okay. It's good. It's supposed that you don't see any changes what I'm doing, but okay. So if everything's okay, we are going to talk about fine dimensional representations, and the topic is Q characters. But let me first recall where we are now. So we are half of the course, or maybe more, we are talking only about quantum affine SL2. I actually plan to talk about more general affine quantum groups today, but still, who knows? This quantum group has Drinfeld realization with generators, which are denoted by X minus, X plus, and also Cartan generators, which are denoted by HR, or when I will talk about different, not SL2, maybe I put R in square brackets as for other modes. Doesn't matter. And now let V be irreducible finite dimensional type 1 representation of this UQ of SL2. The word type 1, let me recall, means that action of the generator K is given by Q in some power. So if you want to write formulas, and it will be V will be sum over some lambda subspaces, another letter mu, subspaces with mu, such that okay, for any zeta belongs to V lambda, K1 and zeta equal to Q plus lambda 1 zeta, and K0 and zeta equal to Q in power lambda 0 zeta. And lambda 1, lambda 0 are some numbers. So eigenvectors are given by Q in some power. In principle, could be some signs in fine dimensional representation, but it is sufficient to consider type 1. Then for such fine dimensional representation, we defined the notion of L highest weight and also L weight. So the vector V is what's called L weight if it is eigenvector for all these HRs. Usually this is denoted in terms of the current. This is written in terms of the current. So we have psi plus of, oh no, today I decided to denote vectors of the representation not by V, but by some Greek letters, psi or zeta. Let it be zeta, because I want to keep V for some other thing. So it is an L weight vector if psi plus of Z on zeta is equal to some function phi on Z on zeta, and similar for psi minus. theoretically speaking, this function could be different, but for n-dimensional representations, they will be the same. As a remark, these equations, okay. So the vectors which we defined above, so this L weight vectors, can be viewed as some version of the beta eigenvectors. So we have a big commutative subalgebra generated by psi plus and psi minus loops to Cartan, and we have the natural question to study its spectrum in the fine dimensional representation. Actually, this is already some version of XXZ spin chain. This is some degenerate version of the spin chain, but I will talk about maybe next time, or maybe I plan to talk about this, but not today. Here, just remarks. So this L weight vectors can be viewed as a sum. Let me state that this is a simple integrable system. So simple means that everything can be solved in this case, but already we have some big system operators. Yes. So psi are exponent of h, and phi these are just some functions. These are functions. On the practical level, they will be just meromorphic rational functions of variables. Now let me recall some facts which were stated last time. As told something about proofs, I plan to write more. I will write more in notes and maybe give you some problems, but now I just state as a fact. So if V is again a finite dimensional irreducible representation, then A exists and unique up to scalar L highest weight vector, which is denoted by psi, such that this highest weight vector means that x plus on this vector x by 0, and the action of it is L highest weight, so we have function phi plus and phi minus, and these functions, okay, we have these equations, psi plus minus on vector psi z equal to phi plus of z on function psi. Okay, then the second statement that exist how it's called polynomial unitary, I think, polynomial P of z, which unit highest so the form z in some power L plus 1 such that this function phi plus of z is equal to q in power L P of z inverse P of Q squared minus 2Z inverse, I think, and equal to phi minus of Z. And statement C that V is tensor product of evaluation representations. Are there any questions? The statement C is the same. The similar statement C holds for Yangian of GL2. And actually, one of the possible proofs of this result is just mimic the Yangian proof. For Yangian, we do not have these two functions, phi plus and phi minus, at least in the definition. So we don't have some here situation. I mean, it's more rich. For Yangian, the current algebra, we have modes in just in one direction. And here we have two functions. Okay, so as a remark, C only for SL2 case, which we can see here, but A and B are hold inseparable. It isn't. I mean, so for other algebras, we also have the notion of L highest weight, also have the notion of Dirichlet polynomials, but it is not true that any representation is standard product of evaluation representations. It is why. Maybe I should also put a work, this word here. So P of Z is Dirichlet polynomial. Okay. Then, of course, the best example which we want can have is two-dimensional representation, C2 of some parameter U. I think I even wrote the formula in some problems that action of psi plus, let me copy it for the speed. This here, this is a part of the lectures. Okay, can copy just. Hope it will work. No, not. Once again. Okay, copy. So in this case, for C2, the psi plus and psi minus of Z acts by this formula. It's just, it can be computed. And here I used another letter V instead of U, which is related to U by this transformation. And this is why I keep V, I denote vectors by Greek letters. Anyhow, so you see that this the corresponding functions are just rational functions. What we can also see that this is the highest weight vector, L highest weight vector. So in this case, the corresponding function is so it's v minus q squared z q v minus z. If you want to rewrite it in form which I said it is possible, which I used in theorem, so it should be polynomial on the inverse, so with the unit highest term. So it will be z min minus here, and here will q minus 2 minus v inverse, and I believe here will be q as expected here. So the theorem states that we have that psi and plus psi minus acts by rational function on the highest weight vector, but it is also true for it is also true for any vectors, as we will see in this example, and actually we will see below. Yes.
Там было 4 материальных элемента. Вот эти функции, они похожи на два диагональных, причем перевернуты как наверх. Там было U1 и U2, а здесь V и Z.
I don't have good comments, so maybe just ignore the question. Okay. Let's consider more another example, which is not C2 of U, but higher representation, also two-dimensional. Let me take the representation some VL of U, where VL is a representation of dimension L plus 1. I denote it by today by psi L minus 2, so psi minus L, and the formula for the action. Okay, maybe for speed I just copied somewhere. Okay, this not here. Okay, maybe here. Here. Here should be not V, but Xi. We have evaluation homomorphism. Now, let me maybe even in this. Okay, I'm not copy explain here. In this evaluation homomorphism, so these formulas which I show you here, they are formulas for fine-dimensional SL2. We want to look the presentation of fine SL2, so we have evaluation homomorphism. Evaluation homomorphism is defined in terms of the Jimbo generators. So, but when we talk about L-weight space, we talk about new realization. So we have to write the all root generators x plus and x minus and for this evaluation homomorphism. So let us compute the action of some E delta under this homomorphism. And here's the computation. So E delta, let me recall that E delta is a Q minus 2 commutator of E0 and E1. Now we substitute that E0 goes to UF and get this. And okay, we substitute everything, and this is the result. I don't think it will help. I don't to look carefully to the computations. Let us look at least to the result. What we have here for Q equal 1. If Q equal 1, then these terms equal to 1, and we have just difference, and it will be m, or better to say it will be minus m. So E delta is something like cartan, but actually not h minus h, because this commutator of E0 and E1, but not E1. So this minus m as expected. Using this formula, we can compute action of any of root generators. This is a computation which I maybe not so important, but this is a resulting formula. Let me copy it. So you see this part is actually the same as here, as we have, and this part is response to loop, but for Q equal 1, we would have that x plus n, it will be u in some power n times our vector. But in this case, we have some Q-related factors here. Okay, using so for this L-dimensional representation, L plus 1 dimensional representation, everything can be computed explicitly. The highest weight after all this computation, the highest weight have the following form. I want to state its form, but in order to say that, but maybe for speed, I also copy it. You see, I have secret file with many computations. I don't know which of these formulas is the best one. You see, we have several versions how to write this eigenvector. In any case, it will be the product of two. We have one linear function numerator and linear function numerator, and difference between roots will be q in power minus 2l. Another way to write it down is the following. So we can take the tensor product v of u in power 1 minus l over 2, tensor v of u q power 3 minus l over 2 times times v of u times q in power l minus 2 over 2, and take highest weight vector here. Maybe you remember, so we see for any two consecutive factors here, the evaluation parameter differs by q squared. In this case, the highest weight vector here generates three-dimensional irreducible submodel. So it's natural to believe that for all sides of this product, the highest weight vector here will generate L plus one dimensional submodel, as in the case for symmetric power. And then the action of psi plus on the tensor product of the highest weight vector will be equal to the product of the functions which we compute to a two-dimensional representation. So we take this. I don't know, maybe better try to take this one. I don't know. So we take product of the function. In this function, which when we look at the function z, the roots in numerator and denominator differed by q squared. If I take tensor product of the L such functions and such that we always have cancellation, then the roots will differ by q in power L, 2L, as should be here. Okay, is it clear? Oh, what I just said. I'm saying that, okay. So let me write it if you want. So I take product of two such functions. One this. And another the same, but with a shifted parameter by q. So here will be q minus 2, here will be q minus 2. And this equal to q squared. And here will be something. Okay. So what I'm claiming that for any, so we can compute highest weight for any finite dimensional representation of SL2, for any evaluation representation of SL2. Now, in principle, we can even. Okay, now let me define the notion of character. Assume that we have a vector which zeta such that psi plus minus on z on zeta is equal to phi of z on zeta, where phi of z has the form which is similar to the form in which we have in the Dirichlet theorem, namely phi of z is equal to q in some power. Have product z minus ai. Here a product z minus by bj, z minus q squared bj. This number is number of i's minus number of b's. I can write it. Then we assign to this vector z, we assign a product of what of EI's times product Y of BJ's inverse. So in general, what we are going to define, we are going to define the map, which will be called Q character. Q character acts from the finite dimensional representations of our algebra UQSL2 to the some algebra which I denote by C of Y. And so this is the algebra with generators labeled by complex numbers. So, of course, it was a very huge algebra, but at least this is what we actually have. And similar to the standard notional character, the definition goes as follows. So we take representation V, decomposed into direct sum of the one-dimensional subspaces. In principle, not necessarily one-dimensional subspaces. So subspaces V phi. This is a. Okay, I need colors. Let this be blue. Now revert. This L weight subspace with function phi. Then this function, which is a Q character of V, is a sum of dimension of the corresponding subspace times Y of phi. Maybe I don't know this, but just by Y of phi. Please bear with me. Are there any questions about the definition? Definition is a bit ad hoc. So of course, but so there is another more natural definition which I plan to talk later, not today. For the practical purpose, this is the simplest one. So we have our commutative subalgebra, psi plus and psi minus. We diagonalize them, and for any eigenvector, we look to the corresponding eigen function, and then consider its look at their roots and poles. Of course, in order to, we have to check that the definition is correct, that any eigenfunction indeed has this form. I plan to explain it in a minute, but before this, I hope the definition to be clear. Maybe I should give some at least example. Here it will be C2 of U. I have a formula for the action of the psi plus and psi minus. Let us now compute Q character. Does anybody have suggestions? Maybe I want to change the sign here in order to have better formula. I think it will be better. So what term correspond to this function? In this function, we have 1, 0, 1 pole and 1, 0, and they differ exactly by q squared. And I want this to correspond to the factor of the first type. So for this term, we have y of a. In this function, situation is similar. The difference is that here we have, how to say, here the 0 in the numerator is a q minus 2 times 0. So 0 in denominator is always v, here and here. And here q minus 2v, and here is q squared v. So this is the y, and this is actually the y inverse. And not corresponding to v, but actually corresponding to q squared. Can I? Okay, is it clear? Okay, can you hear me?
More or less clear.
Why less?
I don't know. For me, I need time to get used to this definition, but these simple computations seems okay.
Okay. Any other comments? Maybe somebody else also can hear me.
Okay, if no one can hear you, then I'll ask a question. So I know about characters of SL2, and especially of two-dimensional representation. Can we extract this simple character from this one, from Q character?
Yes, I will. Yes, I will say in a minute. But
okay.
Yes, I'll see. Before, let me give a remark. I mean, more naive person would ask me, would suggest not to invent such new notion, but just take trace. This is a standard notion of the character. Why not? So, but if you take trace of this function, what do we get? We get qy minus z in numerator, and in the denominator, and in the numerator we get something like y minus q squared y minus z. So we get some number. Okay, I'm not sure that maybe this number. Maybe plus here plus. Okay. So actually this Misha answers to your question, because this is a character of two-dimensional representation of SL2. But some sort of bad news that we lose almost all information about evaluation parameter. So different representation gives us the same value. So this is not too simple. We lost V evaluation parameter.
So it should be something like, I don't know, a trace with some inserted R matrix or what?
So can we define this as a using R matrix and traces?
Yes.
Yes, there is a So clever definition of this function uses quantum L operator, but not today. Yes.
Okay.
Yes. This should, of course, there's some sort of trace, and another. Okay. Now let me restate the definition.
So Misha, sorry, I will ask another question. So, about this R trace. So when we compute invariance of nodes, then we can compute them using R trace. So it's some procedure. We should construct something from R matrix and then construct R trace. Is this R trace the same as clever trace here?
No, I mean by clever trace, I mean that instead of A plus D, say you take just A. So this somehow corresponds to the fact that we have simple integrable system. We study eigenvectors of the just loops to Cartan.
Okay, so I think it is different from what I thought. Okay, so it's not A plus D, it's A. Okay.
In some, yes.
Okay.
It's not clear from this why we have so many summoned, but okay, I plan to talk about this.
Okay.
Okay, let me say, give another form of this definition. It is given in terms of the Heisenberg generators. So if we have some vector zeta such that HR on zeta is equal to, I hope I will write. Okay, let me look to my notes in order to be sure that I'm writing correct formula. Yes, this formula which I wanted to show you. So if HR on some vector psi zeta have the following eigenvalue, then we assign to this vector the term which is a product of AI times product of by I. Of course, it is easy to, I mean, you have to believe me that I didn't make mistaken computations, but it is clear how to get from this to the phi, which is because psi is just exponent of the Heisenberg. So exponent of the sum will give us something. Just in case, which formula do you prefer? I prefer this formula for the following lemma. Assume that we have some vector zeta such that x minus n on zeta is equal to x minus n, x minus 0 times some number gamma in power n on zeta. And I try to explain that for any evaluation representation, this is true. This gamma depends on zeta, but it's what we should expect from evaluation representations. Then the vector x minus 0 of zeta is again eigenvector for HR with the eigenvalue as before minus Q gamma power minus Q inverse gamma power. Okay, let me denote just this vector zeta prime to be x minus 0 of zeta. Indeed, how to show this? So we so if you want, of course, if it is true that this should be straightforward computation, we act by HR on this number zeta prime, and so this HR of minus 0 zeta, so it is x minus 0 HR zeta plus we compute commutator of HR and x minus 0. This commutator equal, of course, I don't, maybe nobody remembers. We look to the formulas for the, we have to find somewhere formulas for the commutation relations in Newton realization. Here it is. Now case k is 0 to R minus R. So here we have minus 2R over R, x minus R zeta. And now we just substitute this formula against this. So for finite so in terms of this Q characters, it means that we have some monomial and obtain U monomial, which is differs from the first one by 2 y's inverse, y gamma, y inverse gamma, Q inverse gamma, y inverse Q gamma. Using this, we can write Q characters for any evaluation representation of SL2. Let me state the result, or better to say copy it. Here are the formulas for the first two, and generic formula is the same. So if we take VL, cos of U, and here and here. So it will be first term will be product of L minus of L y's which starts from the V Q minus L I made in brackets. Probably I somehow missed the notations because here, but I can change it now. And okay, and for any representation situation will be similar. So we have the first term, which is product of L y's. Then we get terms which will be product of L minus 1 y's times y inverse. Then we get 2y inverses and so on. And the last term we will get product of L y inverses. And the arguments can be computed. Now let me state, let me look to my plan. Okay, now let me state the important property of these Q characters. Proposition. If we have two irreducible representations, no, not necessarily irreducible. No, sorry. Let V1, V2 find dimensional representations. Then Q character is equal to product of their Q characters. Before proving this, I want to say some more words. First of all, okay, let me give a corollary. This corollary can be explained in different manner. Okay, it can be explained in different manner, but let me state it here that we have the following commutative diagram. So we have representations, finite dimensionals of UQ SL2, which maps to finite dimensional representations of UQ SL2 without head, just ignoring some structure. From this we have mapped to Q characters, and from this we have mapped just ordinary character, which from one variable which we denote by y. And you have a map here which maps any y of A to this y. And corollary is that this diagram is commutative. And moreover, if I write here K0, so I consider Grothendieck ring, which is a ring with respect to direct sum and tensor product. Then, so the proposition means that this arrow is a homomorphism, or algebra homomorphism. And so this is a commutative diagram of commutative, just now associative algebras. now associative algebras. And why this corollary is true? Because due to the fact C, any it is sufficient to check that for irreducible representations, and due to the fact C, it is sufficient to check to the tensor product of evaluation representations. And for just evaluation representations, we see from this formula that if we take Q character and then replace forget each index, each argument of Y, we get ordinary character. And from this proposition follows that for tensor, then we have the same for tensor product. Q characters multiplied and the ordinary characters are multiplied. So if after the forgetting the arguments, Q characters for evaluation representations coincide with the ordinary characters, then for the tensor product it is also true. Questions? Who else can hear me?
I can still hear you.
Anybody else can hear me?
Да, все понятно.
Да.
Okay. Misha, you have more questions or no?
I don't think so.
Okay. I should also say that it is no need to prove this proposition in order to state that if we, without talking about algebra structures, the diagram is commutative, but let me at least now put it like this, and maybe then I will correct it in slides, give another proof. Now I want to prove the proposition, just in order to prove something in the lecture. But let me, for simplicity, prove it only in the example. So let me assume okay, let me say that which formula we will actively use, what formula we will use, and then I give the some details. So we will actively use formulas for product, and I will use this formula. All formula. This is a formula from lecture 6. Believe me or not. This formula says that delta of the Heisenberg algebra is a consists of standard term plus corrections Okay, maybe just So let us assume that one of these representations is so this V1 is a C2 of U. Maybe better write because not V and V tilde. Oh, V tilde and V. Okay, I change notation. Rewrite it. V tilde as a first factor, and here, so let me assume that V tilde is just two-dimensional relation representation. Then for V tilde, we have a basis of two vectors, v1 and v minus 1. And for v, we have some base, not v psi. Sorry. We have some, it's some of its bases. Here have its, or maybe without tilde. Let me write here. Zeta 1, zeta 2, many other vectors. Now we use this formula. This is triangular property of the Drinfeld-Jimbacher product, which I claimed in the lecture 6, and now I wrote more in the notes, which I posted. I wrote more notes and so added a reference. And if somebody's interested, I can explain the full proof. But now I just use this result. And this result, what we have, if we act by delta of HR on the tensor product, psi1 times any zeta k. Then we get, first we get HR psi1 tensor zeta k. Second term is psi1 tensor HR zeta k plus 0, because all this u plus the combination of the vectors from x plus, and x plus vanishes psi1. So this tensor product of psi1 of any of these vectors, if I assume that all the zeta are eigenvectors of the Heisenberg of this loop algebra H's HR, then this naive tensor product is also eigenvector of the HR. So I assume that these eigenvectors, these are all L-weight vectors. If I compute delta of HR acting on the another product, I get the same term as here. Okay, let me just copy. Plus here not 0 in general, so we have u plus, but this u plus acts from psi minus 1 to psi on. So plus, so we get plus psi 1 times or something. And in order to find eigenfunction of HR, it is not necessary to compute this. You can, okay, it is not necessary because we see that our matrix now becomes of HR becomes triangular. So this here's the vectors of psi 1 times zeta r, here psi 1 times psi minus 1 times zeta r. And here the matrix is diagonal. So we compute this diagonal part, we compute this diagonal part, and that's it. And the diagonal part here in terms of H is just sum of the eigenvalue of HR here and eigenvalue of HR here. So in terms of this definition, for one we have some set of A's and B's, another we have some set of A's and B's, and they are just we take the union of the set, which correspond to the product of this Y monoids. So this is the end. Questions? Okay, as a remark, let me say that everything will be simpler if we use Drinfeld product. In Drinfeld product, there is no such term. in the Greenfield product, which is defined just from the beginning defined in terms of loop generators. There is no additional terms. So the eigenvectors will be just the tensor product of the eigenvectors. And here eigenvectors constructed from this standard product are triangular with respect to naive tensor product. So we have some triangular matrix which maps from the one eigenvector basis to another eigenbasis. So how to say? So L weight vectors are just products. So it means that if we take tensor product v times v tilde times v, it has two different structures of the model of the quantum fine algebra. One with respect to ordinary coproduct and another with respect to Greenfield coproduct. Okay, let me write it here. So we have v tilde times v with respect to delta. And we can take v tilde times v with respect to Greenfield coproduct. And for general values parameters, modulus are isomorphic. There is a matrix which permutes them. And this R matrix is triangular in this L weight basis. Because for Greenfield coproducts, L weight basis is just a product of the basic vectors. And here our matrix which we obtained is triangular, and some matrix which maps one base to another will be also triangular. And actually, this is the algebraic incarnation of the stable envelope, which was defined in work of Maulik-Penkov. This is triangular matrix. Of course, this was known much long before, and their contribution is geometric and high generality and so on. But just to have some words. Okay, I just think it was too much. Okay. If there is no question, let me summarize what we said above in the following theorem. Key theory of finite dimensional representations of UQ SL2 is an algebra generated by YA plus Y This fact should be compared with the fact that finite dimensional representation of the, say, GLN is an algebra of polynomials of n variables. Because for each representation we can assign the characters, and the characters form a basis in the algebra of symmetric polynomials. here we for any representation we assign a Q character and define some algebra, and this algebra is also symmetric polynomials. We have SL2, so we have only one reflection, but now reflections act like this. I said that we summarized discussion before, but to be honest, we didn't prove it, even up to some facts which we assumed and so on. Let me comment what arguments remains to state. So we have a map. So we have a map, a Q character map from K0 of this to the C of Y. Now, this this is a Q character of two-dimensional representation, evaluation representation. So the image contains these elements. They belong to image. Now, I claim that any Q character of any evaluation representation belongs to this algebra. So maybe I should organize it as a number of bullets. Bullet number 1, bullet number 2. We actually computed this Q character, so it should be just checked. Let me explain it on the case of three-dimensional representation. So for three-dimensional representation, this is the formula for Q character. And this is equal to the product of this is equal to the product of one Q character times another Q character minus 1. This should resemble the clear statement that, clear the statement which we already made, that the tensor product of two evaluation representations with parameter related by Q squared is contains a three-dimensional submodel, and the quotient is one-dimensional. So this is pretty much the formula. Okay, are there any question about this bullet? So we proved that for that we have a map. We proved that its image indeed belongs to the space. It remains to explain that this map is injective. And this is for the following reason, that any okay, because for any finite dimensional representations which is constructed from some trinity polynomial v of p, the corresponding q character is a product of, if p is a product of ai, so it is a product of y characters plus, as usual, low terms. So low terms, it is the terms where we have less y's. Low with respect to the finite dimensional L2 character. This is because, again, we can use, for example, the fact that any representation has a product of two-dimensional evaluation representations, and for evaluation representations, we already know this. And if you assume this, you can see that obvious triangularity property of the Q characters. Each we have basis. How to say? So these elements are linearly independent for all Greenfield polynomials. Therefore, Q characters are linearly independent. Therefore, this map is injective. So Q characters of irreducible representations are linearly independent. Hence, Q characters of irreducible representations, irreps, are linearly independent. And that's it. This is more or less all what I wanted to say about SL2. Just as a remark, I don't know whether it will be useful to anybody, but this formula y plus y inverse, is somebody, okay, maybe I put it as a question. Did somebody heard something about deformed Virasoro algebra? I mean, something like Bazanization of deformed Virasoro algebra. Okay, so okay, this should resemble. This actually resembles deformed Virasoro algebra, and actually I can add some screenings to the story, but maybe instead of this, I just say a few words about generic algebras. Maybe no, maybe I will not do this because it's just 5 minutes. I will stop with comments. So I have 2 remarks. So first remark that this should resemble deformed Virasoro. And another remark. Let me denote the product y of, I have prepared notation. probably this notation by A of V to be a product. Then we have a Q character of the evaluation representation has the following form. We have monomial, so product of y's times 1 plus low terms. And these low terms are monomials of a's. You can, of course, think that difference between i's and a's, the a's correspond to simple root, maybe negative simple root to the root, and y correspond to the weight. And a this minus stands for the a's negative weight because we go from the highest weight vector. And the formula is like this: we have some a with some argument, then 1 plus again new a, and so on. And again, if somebody shows something, some cluster formulas, this is a typical formula story, and this is actually some hint that we actually have some cluster structure. Where I is a monomials and y's are y's. Okay, I have no short remarks, and it is useless if I start talk about generic G now. So let me stop here, and maybe next time I'll talk about Q characters for generic algebra G.
Сейчас, насчет кластерной структуры, а тут есть какие-то мутации?
Да. Это
А как они
категорификация. Там это написано через некоторые точные последовательности. This is so-called monoidal categorification of some cluster algebra.
Спасибо.
Just this is not answer to the word. And references the paper by Leclerc and Hernandez. Papers by Leclerc and Hernandez. They have some, I think, a couple of reviews about the story. For SL2, everything is quite simple. The main achievement of the works is, of course, generic G. Other questions? Okay, if not, let me stop the recording.